So today I'm going to talk about a mathematical function I discovered that explains how our minds, music, and mathematics all connect and how they interpret beauty in the world. It all comes together quite seamlessly. And it's a simple but profound function that has a lot of implications. It's hard to not make your brain just go crazy when you start looking at these patterns. And it's a function the ancient Greeks probably would have came up with if they had computers, but they didn't. So now we're here at George Mason listening to me, and buckle your seatbelts, you're in for a ride. So it all starts with a simple but profound question. How do we know which notes sound good? It seems to be something we're inherently just born knowing, dun, 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 dun. But there is some sort of mathematical relationship to it. And let's start with the obvious. It has to do with what scale you're in. If you're in C major, and you just play it sounds like randomness. There's no mathematical symmetry to it anymore. So the natural question to ask next is, how did we come up with scale? Well, that starts with Pythagoras. He's the ancient Greek philosopher that, you probably know him as the guy who came up with the Pythagorean theorem, a squared plus b squared equals c squared. But that's not what we're talking about today. He came up with this idea after walking across a blacksmith shop where he heard 3 hammers pawing some metal prongs, and he noticed something. Hammer A made the note, hammer B made the note, hammer C made the note. So he noticed that when hammer A and hammer B were played together, it sounded pretty good. Hammer A and hammer C played together, sounded pretty good. But then hammer B and hammer C played together, not so good. Sounds pretty bad. So he rushed over to the blacksmith shop and started wondering and wrote down all this stuff. And eventually, to simplify it, he realized that it all had to do with the ratios. It all had to do with the space in between one octave to the other octave. That's all the notes in between those 2 octaves. And the 1.3, that's a perfect fourth. 1.5, that's a perfect fifth. And then 2, that represents an octave. It all had to do with the different string lengths. Quite fascinating. So he kind of went on this idea and went kind of cuckoo. He invented this idea of the music of the spheres, which is this metaphysical ancient Greek philosophy that everything in the universe is made of these divine proportions and everything can be represented through these mathematical symmetry, just all based on ratios, and it creates beauty in this world. But you get into a problem kind of fast when he discovered that the square root of 2 is not a rational number. There's no way you can represent the square root of 2 as a divisor. It's in one number over another one. It leads to a contradiction. So that music of the spheres philosophy, fell into trash. But his tuning system went on till the medieval times. But then the medieval instrument makers ran into a problem. Okay, when you're playing with Pythagorean tuning, you go from one scale, you can't seamlessly change from C to D to E to B flat because all the ratios no longer are these in perfect symmetry anymore. So they invented equal temperament, which spaces the notes evenly through powers of 12. So you no longer get the beautiful, simple harmonic patterns, but it's close enough where your brain recognizes it as music. So what happened? One day, I watched a YouTube video by 3 Blue, 1 Brown, and he's this math dude that makes all these really cool, entertaining math videos that I give a lot of respect to. He teaches you about linear algebra and all these cool videos in math in a cool way. And so he had this video called Music and Measurement Theory. And he explained how the simpler the ratios were, it correlates with what notes sound good. And it all made mathematical sense. He used set theory and all the spaces between 1 and 2, and similar to what Pythagoras did. But there was one problem. He wasn't able to list exactly what the Pythagorean ratios were. It was only an empirical hypothesis on how we recognize which notes sound good. If they're close to the Pythagorean ratios, they'll sound good, but you couldn't list the Pythagorean ratios. There's no function yet known that could list them. So one day I go crazy, but I had an intention. I had some purpose to what I was doing, I swear. I basically just list the Pythagorean ratios from the simplest to the most complex. From the perfect fifth, perfect fourth, major second, minor seventh, major sixth, minor third, minor sixth, and so on. And I realized this function could just keep repeating. It didn't stop just when the octave stopped. It kept going and giving you more and more ratios. And I also noticed that all of them could be expressed as powers of 2s and 3s. And there's also this interesting flip-flop pattern that seemed to happen here. So I'll get more into the math in a second. But I've noticed something interesting, that the pentatonic scale, the most universal scale heard throughout all cultures, just popped up in the first 5 numbers, just every other ratio place, starting at the 3s, if you recognize it there. That's the pentatonic scale. It's 5 notes per octave. In the major scale, minor scale, they seem to have some sort of pattern to it. So I was determined to dig deeper. And I realized everything here could just be generalized. Every ratio times the sequential ratio always equal 2. And if you see algebraically, that makes perfect sense. The 3s would cancel out. And then the 2 to the nth term will cancel out. So you're left with 2 to the 1, which equals 2. And that is true every time, through every sequence of this ratio. But I had another problem. I couldn't figure out what the n term was or how that related to the x term. It seemed to increase in this weird order. So thinking like a computer scientist, I kind of came up with this truncated method, which is if after the 2 to the over 3, and you flip-flop that, and you add another one to the x to the 3rd term, you have to check if that term is greater than 2. And if it is, just add another one to the n term under the denominator, and then it would decrease it back down to a ratio between 1 and 2. And if it's not, then just leave it the same. And the pattern continues. You're left with this simple algebraic fact. So what do I do from here? I start graphing them. I want you to take a second to look at that and just look at that, I forget what it's called, the ink blot test, your Rorschach test almost, where you just can look at that pattern and you're starting to just see all these things in nature that it just reminds you of. It could be some DNA structures, some molecules, or something's going up with that. It has this weird symmetry and not symmetric. Something's going on with that. And it works with other numbers. Not just 2 and 3, works with the 2 numbers entered could be any number. So I tried it with 3s, then I tried it with 5s. And there's some pretty remarkable stuff I was getting, and I figured it was worth looking into. So long story short, I got some help from my math professor, and voila, the Fustero function. It kind of rolls off your tongue. Where I put n in terms of x, using the upper integer bound of x times the natural log of j divided by the natural log of k minus 1. And ladies and gentlemen, you could take that to a very, very, very large number, input the x term into this, and then you put it back in the function, it will always be true. This is a mathematical fact. And if you're just a little confused, I put some nice arrows pointing out that the j over k term is the a sub 0, a sub 1, a sub 2. And then the k over j term is the f of a to the f of a to the 1, f of a to the 2, and so on. So if you enter k equals 2, j equals 3, voila, you get the Pythagorean ratios, all in a simple, neat list. And using just that, you can check it on your calculators when you get home. You don't believe me. So if you think about what this function really means, what you're really doing when you think about it, what your brain's doing when you're listening to music, you're considering how many 2th dimensions, how many 2th dimensions are in this 3th dimensions, and you're multiplying that or counting in terms of how many 3th dimensions are in 2th dimensions. And it always equals 2. And if you kind of go more abstractly with it, which I always do, you can think of the 3s as a spatial dimension and 2 as like the time dimension, where you start from one point and you go to the second point. And your brain is constantly living in this past and present mentality simultaneously. So how I kind of think about it is your brain is just constantly looking at this contradictory pattern and constantly doing these computations to make sense of it. And how your brain's interpreting these sound waves coming to you is a very pleasing symmetric form of how we're moving through time and space itself. So the next thing I did was I put it in polar coordinates. And I want you to notice something that jumped out to me right away. That pentagon in the center. Remember what I told you about the pentatonic scale being the most universal scale in the world where every culture uses it? I want to make an argument that the pentatonic scale is just an artifact of how our brain interprets reality itself in the first place. And you can see just through the first 100 iterations of my function using polar coordinates that you get a pentatonic shape. There's no hiding that fact. So let's go to the next function. This is 5 and 6. And you get this kind of rosary pattern. It's pretty interesting. I know what you're all asking. Can you put some detail in it? All right. So now you really see how all the lines are connecting. By the way, ladies and gentlemen, these are all straight lines. I programmed this by putting the opacity of the line very, very, very light and then iterating it over the function 7,000 times. And then where it's darker is where the lines crossed each other a lot more than it did in the other ones. Where you see the lighter lines are where it just vaguely touches each other, and then the darker ones are where the lines are boom, 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 intersect, intersect, intersect. That's 7 and 8. That's 7 and 13. That's pretty crazy. That's 2 and 3. If you notice, and you go a lot of iterations, that's the Pythagorean ratios. You don't really see the pattern anymore. You just see this general white circle in the middle with a darker circle out on the outer side of it with another lighter circle on outside of that, vaguely, with all these kind of weird elliptical curves. So what I would like to do is create like a GIF where you see all the lines connecting as you keep moving forward, and then you'll be able to see the pattern a little bit better. So this is with 19 and 24. One thing you should notice is that as you increase the number, the radius of the circle will get bigger and bigger. It's kind of like a donut shape. So the circle in the middle will always have a diameter of 1 because those are all the numbers between 0 and 1, and there are no ratios that are less than 1. The music tuning system, because that wouldn't make any sense. And that's 3 and 5 really close up. And so it's just interesting to look at, and you can get mesmerized by them. So here you are, the Fustero function, and I kind of want to make a proposal that we should rethink the music of the spheres idea. I think the ancient Greeks are onto something. They just missed the whole part about having an algorithmic with a ratio-based universe. I think this idea of the music of the spheres with some computation and discrete mathematics combined with each other can paint a very beautiful picture of the universe. And it's an idea that should be taken seriously mathematically, scientifically, and philosophically. So maybe our ancient Greek ancestors weren't so cuckoo after all. Thank you. Any questions? Okay, cool. Question time. Yay. I guess it question. All right, hit me.
How did you graph the function?
Say it again.
What did you use to graph the functions? Like, that didn't look like a calculator. How did you make the...
Basically, I used Python and this program called SVG, right? Scalable Vector Graphing, which is it's just a way to put it in a different sort of file so it doesn't export as PNG. You can do more with it. You can zoom in a lot closer. So it doesn't just give you this bit rate kind of map. You can now zoom into it and see it very closely and then also very far away. So if you look at JPEG images and PNG images, they always have a bit rate to it. But this is more like a PDF file where you can zoom in really close to the text and it won't screw up how all the text looks. So it's a way of just doing it without that.
Also, what implications do you see this having for music and music theory?
I would love to put this through an analyzer and see how simple songs like Twinkle Twinkle Little Star or anything could be played going through the notes that it is and just seeing the different shapes that music makes. So it's a way of you can theoretically inverse the process, make shapes through that graph, and then turn the other way around and make songs with it. And before using it, I've never seen a very good plugin. You just using Photoshop. It's always tend to make crappy sounds. So that's one of the implications.
Anyone else?
No.
Do you have any other comments?
I could. If you remember what I said about how this always creates a dark center, but this circle is always in the middle, having a diameter of 1. And if you increase the function more and more, the circle around it will get bigger and bigger and bigger and bigger and bigger and bigger. If you keep extending it, and just for the sake of argument, assume that it goes through it an infinite amount of times. So it would be a completely dark circle if it just goes through an infinite amount of times because every point has to be touched. Now, what would happen if it goes through an infinite amount of times? Because the outer part of the circle would have to be infinitely big, but you're still left with an infinitesimally small white circle in the middle with a diameter of 1. So it seems to be this contradictory idea that would be a completely filled dark circle, but yet have a very small point in the middle that it has a diameter of 1. So how did this work? Well, it's actually resolved quite simply in the mathematics. Because if you put infinity in terms of k, you get something divided by infinity, which equals 0. So 0 times anything equals 0. So just visualizing it itself, you can see, oh, what is something that'll go infinitely big and then fill up itself? Well, it's actually a paradox very easily resolved in the mathematics. If you just put it through put infinity in it, you see it's times by 0. So it's very interesting. I think that's one of the more abstract sequences I've looked at. It's just when you put 0 and infinity into this sequence, you get an infinite list of zeros and infinities. So it's kind of cool. That's one of the cool things. Anyway, I guess that's it. Oh, question?